Really?
Otherwise, I would have taken a lot of time.
I've had like
Yeah, sure.
It's like far out. It's far. It is like.
See, you made a mentee for
same thing.
But they said like a.
It's like
Yeah, honestly, it's just
Yeah, I could do it.
sounds very weird.
Man, they basically like
Guild, but like
change it.
Oh, yeah, that's the name.
Something in 13.
that means a fun like
I can do the color.
Hi everyone, can you hear me? So thanks for coming today. So today is our fourth lecture. So we will introduce custom kernel integration and AI hardware. So it basically contains two parts. The first part, I will briefly introduce what is the motivation of designing custom kernels and how to integrate this into our front-end machine learning framework like PyTorch and TensorFlow. In the second part, I will introduce AI accelerators, AI hardware. Basically, I will introduce a systolic array, which is the basic compute units in Google TPU. So I will introduce their different data flow or string flows. So before we start, there are two updates, and the first one is I think I received some feedbacks on. Sorry, I think this is not working properly. So, but sometimes you might see the back screen, but just it will come back, recover very soon. And so the first update is I received some feedback saying the content is too dense. Right? So I will try to mark in the slides if some particular slide page is not accessible, so I will let you know. So this is the first update, and the second update is we will have the lab session next week, starting from next week, next Thursday. So so I will also release the coursework next week, and the coursework will only about the CUDA programming. So it will not. So today we will introduce Triton, but it's more like some knowledge I want you to know, and I want to highlight again. So during the exam, I will not ask you any CUDA program or Triton program, and CUDA is will be only useful for your coursework, and Triton is just the knowledge you need to know, because I guess this is the graduate level module, so. The more I want to teach is kind of the skill sets which will be helpful when you go into industry or doing research in the future. So these are two updates. And before we start the module, the content today, let us just recap. What we have learned last week. And in last week, the main topic is GPU, right? So before we introduce GPU, I introduced some basic concepts. First is different types of parallelism. So we introduce instruction level parallelism. So recall what we have in the early version of CPU, which follows the traditional Van Neumann machine. So we execute instructions one by one. So there's no parallelism. However, we have another architecture called VLIW. So it can kind of decode multiple instructions in parallel and issue this instruction for parallel processing. So this is one type of parallelism, ILP, instruction level parallelism. And the second parallelism we introduce is thread level parallelism. So this is the parallelism that CUDA or the GPU programming exploit a lot. So basically, you will have multiple threads, and each thread will have their own instruction strings. And for the third type of parallelism is the data level parallelism. And I list an example as the vectorization, which is commonly used in modern CPU. And we also introduced the Mike-Bling's taxonomy. We introduced the SISD, single instruction, single data, SIMD, single instruction, multiple data, MISD and MIMD, so multiple instruction, multiple data. And then we briefly introduced the history of GPU. So GPU was invented at the beginning as the graphic accelerator. So you can see the 5-stage pipeline of the rendering. That is the original purpose of GPU. And later on, up to the turning point of AlexNet, which was trained on NVIDIA GPU. So NVIDIA tried to put more and more AI compute resources on their GPU. And after that, after all these prior knowledge, we start to introduce the GPU architecture of programming. We first introduce what is the TPU GPU computer architecture. So here I show this picture. So as you can see, all the green part, they are compute resources. So they have the CUDA core, which corresponding to with integer 32 and floating point 32 cores. And we'll also have a separate FP64 cores. And we'll also have Tensor Core, which we introduced, was designed for AI workloads, like matrix multiplication and sparse matrix multiplication. And we'll also have different memory in this GPU memory hierarchy. Remember, it follows a triangle memory hierarchy shape. So which means you have a large amount of register files, and then you have the L1 cache as a shared memory, and also L2 cache. And at the bottom, you have a global memory, which you have large amount of memory capacity, but the access latency is very high. And then we introduced the SIMT, single instruction multiple threads programming model. So basically, in this SIMT programming model, you can control threads, multiple threads, using the thread index as the built-in variables. And multiple threads groups together to form a thread block. And multiple thread blocks forms together to form a thread grid. So this is the basic idea of the programming model of GPU. So basically what you are doing is you try to separate, let's say for a given algorithm, you try to separate the computation into multiple subtasks or subprocess. And you try to issue or assign each subcomputation to each thread using the built-in variables, thread index, thread block index. So this is what we covered, and at the end of lecture last week, we also introduced an example matrix multiplication, which we tried to apply some GPU optimization, like the memory collapsing, to improve the memory access efficiency. So this is what we have covered last week, and starting this week, so we will start to teach you why we need clustering kernel. So you might wonder, because now most of machine learning frameworks, they already provide high performance kernel implementation and libraries. Why do we still need to learn how to use CUDA or how to use Triton to do with kernel implementation? So here I list 3 scenarios why all the knowledge we learned in last week and the module we will learn in this week will be helpful. So the first scenario is when you have new architecture. For example, NVIDIA, they introduce new GPU every 2 to 3 years. Like they have for example, last year or this year, they introduced the Blackwell. So they kind of follow different GPU architecture. For example, they have different amount of shared memory. They have different amount of CUDA kernel or CUDA cores. And this kind of hardware specification, they are changing by different GPU architectures. So let's say when you buy a new GPU, let's say B200, and you want to adopt your old GPU kernel to this new GPU architecture, you actually need to do some. Actually need to tailor your old GPU kernel to this new GPU architecture because they have different compute capacity and memory capacity. For example, in older version, perhaps it has larger shared memory, and you design the kernel that fully exploits this large shared memory capacity. But in the next generation, they might reduce this shared memory. So that means you need to redesign the kernel to improve the efficiency. So this is the first scenario. And the second scenario is every time when you develop new algorithm, which means, let's say you think this self-attention, they are not efficient enough. So you want to self-propose some new algorithm, for example, member architecture, to improve the performance. But if you try to, it's easy to implement in high level like PyTorch. However, when you try to scale this new algorithm to large scale, let's say if your kernel runs too slow, it will kind of, let's say you need to train your model like by 1 month or 2 months. This is not a good case for you to explore this new algorithm. You need to know the underlying hardware, and you need to know how to develop your custom kernel to improve the training process. And the third scenario is, even you are not considering new hardware, even you are not considering new algorithm, you might still need this custom kernel. So here I list the example of flash attention, which is an efficient kernel implementation for self-attention. So self-attention was proposed back to 2017, and this flash attention was proposed by around, I think, 2021 or 2022. So they're trying to propose the highly efficient kernel implementation for an existing operators. So you can see it still has a lot. You can still save a lot of money. Let's say you can reduce or speed up this throughput of this self-attention by 2 times. You can actually save your money. But let's say you try to rent some GPU hours from cloud, and if you can run this kernel fast, you can actually save the money spent in training. So in today's module, I will try to convince you why we need custom kernel, and I use an example of flash attention. So today's lecture, we will only cover flash attention version 1. So if you can see latest slide, they actually have a different version. They actually have version 2, version 3. And in today's lecture, we will only cover the version 1, and we'll leave version 2 and version 3 as the third reading. So if you recall what we have covered in our first lecture, the computation of flash attention looks like this. So first of all, you have this input tensor, and you do different linear projection to get QKV vectors, right? And then you kind of multiply Q with K transpose, you get this attention score, and you do masking, and you do softmax, and you multiply this probability with the V vector, and you get the final answer, and then you do another round of projection. So this is the main computation involved in self-attention. It contains up to 6 operators. So if you look at here, this line graph, so if we don't apply any optimization, so we kind of execute each operation one by one. So you can see here is the time, the execution time. So you will have, let's say, around 2 seconds, 2 milliseconds for this matrix multiplication, which is corresponding to the linear projection and QK multiplication. And you have this masking operation, and then softmax, and sometimes some self-attention module may have dropped out. And you also have another matrix multiplication for P times vector, V, the probability matrix times the vector matrix. And you also have the output projection. So this is the execution time if you don't apply any optimization. And the key idea of flash attention, actually the basic principle we have already covered multiple times throughout this module, is called operator fusion. So which means instead of accelerate each operator one by one, So if you recall, in the traditional store memory architecture, if we accelerate each operation one by one, let's say this is our compute core, and this is our memory. For each operator, we need to involve the memory traffic. Let's say for matrix multiplication, we need one memory traffic send the data into this core, compute core, and we need to send the data back to the memory. And for the next operation, we need to do it again. So basically, if you don't do this operator fusion, it kind of involves up to 5 times of memory traffic between your compute core and global memory. Let's say this is your global memory. And the core idea of flash attention, the first core idea of flash attention is operator fusion, which means we have, let's say, 5 operations. We just design a fused kernel such that after we transfer the input tensor to its core, we just keep all the intermediate results. For example, the intermediate results after softmax in on-chip memory. For example, you have either shared memory or register file, which is DRAM. So you just keep all these intermediate tensor to on-chip memory. So it kind of save a lot of memory traffic between global memory and the compute core, because you try to eliminate the data transfer between global memory and compute core by caching all the intermediate results to on-chip memory. So in this case, in the fused kernel, so we only need 2 times memory transfer. Let's say this is an ideal case. And this is the first idea of flash attention. And once you try to implement this fused kernel on this self-attention module, you realize it's very challenging, because recall, like usually we have large sequence lengths. Let's say this sequence length can go up to thousands. And if you do this operator fusion, which means you need to cache all the intermediate activations associated with these let's say thousands of tokens in on-chip memory, which is SRAM. However, remember we have a triangle, so we only have limited amount of SRAM in on-chip memory. So which means we have to do with the second key idea, the second technique called block tiling. So we try to block this QKV to multiple chunks, and we only cache one chunk at a time to reduce the on-chip memory consumption. So this is the idea shown in the middle of the figure. So for example, this is your Q vector, K vector, and V vector, and this is all your output vector, right? So the basic idea is we kind of separate this into multiple blocks, and we only cache this orange small block. We only cache one block, one tile to on-chip memory, and we try to iterate, like every time we try to load different tiles to do one computation. And if you look at the pseudocode of self-attention, so you can see here, for the line 3 and line 4, it actually do this block tiling. It try to do what exactly we shown here. So we try to block this KVQ into different blocks. And if you look at this for loop, so line 5 and line 7, you realize they put the block tiling of the QK to the outermost loop, which means they cache one key and V block and try to iterate through different Q and output block. So that's the reason why you can see in here. So that's the reason why you can see here. This is the inner loop. So this is the outer loop. So which means they cache one block of KV and they try to load different blocks of Q and different blocks of output matrices one by one. So this is the inner loop. And then when they finish all the inner loop, they will try to iterate next to next block. So you have here, you have another block here, and you do this in the loop iteration again. So this is the second idea. So can you observe any issue for this block tiling? Like this block tiling, they are great. Exactly. So when you calculate the softmax, so if you remember in our first lecture, I mentioned this softmax is basically applied row by row. So which means when you try, let's say you get this attention map, and you try to separate this attention map into multiple blocks. Let's say this is the first block, this is the second block. But if you apply this softmax, let's say in the first block, you need to get the max value to do the exponential operation, right? And the max value of the first block might not be the same as the second block. Let's say the max of the first block E1, and the max of the first block E2. This will lead to different results for two different blocks if you do softmax independently without considering later. So that's the trick they are doing, and also which is one of the most important technique that they propose in flash attention V1. They decompose the large softmax with scaling. So in the literature, we also call it algebraic aggregation, which means instead of just doing softmax independently, we also track some statistic. For example, here, when I apply the softmax, I get E1. And when I apply the softmax on the second block, I try to track the statistic of the difference between the max value of the first block and the second block. Which means when we calculate the second block, we will kind of track some statistic. For example, we track E1 minus E2. We know the difference also. So we know the difference between the first and the second block. So if you remember here, when we do this, if we keep tracking this E1 and E2, and when next time, when we load this tile back to on-chip memory, we can apply this renormalization to make this number correct. So this is the second or most important idea of flash attention, which they try to call it. So this is not new technique. It was well studied in the literature, but they just apply this technique to flash attention. And the third technique they're introducing here is called recomputation. So remember here, what we're doing is we kind of fuse all operations, let's say these 5 operations together, and we do this computation in SRAM, which means some intermediate result, for example, in here, so we have the score, we have this probability matrix, which are not transferred back to our global memory. So when we do this back propagation, if you recall, we have the backward DAG. We need the derivative with respect to each tensor. However, we don't have all these tensor. For example, we kind of don't transfer all the intermediate results back to this global memory. So this is the third key idea I introduced in flash attention, which called recomputation. So basically, what they did is they just keep the still in the global memory. They still have this. They only have the input and output of this fused operator. However, they also use this. They also keep all these statistic, such that even you have the partial of your, for example, one block of your output matrices, you can still calculate the original, the whole output matrices. So this is the third idea. They call it recomputation. So the issue is to overcome the problem which in the global memory we don't cache, don't store the whole matrices. So this is the 3 key idea introduced by this flash attention. And so this is pseudocode. Let's just look at the pseudocode one by one, line by line. So as I said, first you need to do this block tiling, which block your matrices into multiple blocks. And as I said, so you need to do caching. In here, in the outermost loop, we first cache KV blocks. And then we iterate through this query blocks and these output matrix blocks. And we do this fused computation, which means all the computation here is performed in object memory. All these sub-blocks, they are already available in SRAM, which we can access very quickly. And then when the number is ready, we just transfer the result back to the global memory. However, so in here there's an extra operation which they try to calculate. As you can see, they try to calculate all this statistic, which is used for the algebraic aggregation. So they keep tracking all these statistics to ensure, like, next time when they load different Q vector and output vectors, they can try to do this normalization. So this is the key idea of flash attention. And as you can see here, so we track the softmax statistic. And I encourage you to have a memory access analysis on this flash attention. They actually mentioned in their paper. And they try to because in here you still need to load your the data from your global memory to shared memory multiple times, because in here in the innermost loop. And in the paper they try to analyze the memory access compared with the standard self-attention. And I encourage you to do this by yourself and see, like, what is the reduction in terms of memory access. And the paper link is already in this slide. So this is flash attention. So they actually improve the performance a lot. And that's the reason why we need to learn the custom kernel integration. And there are basically two ways to do this custom kernel integration. The first one is you run a CUDA kernel, which usually leads you to hire a high performance CUDA kernel, but the advantage is you need to spend a lot of time in this CUDA kernel development. And another way to do this constant kernel integration is through Triton. This is just one way. And compared with CUDA kernel, so the advantage is Triton is it involves less amount of development time because it's abstract away a lot of low-level details. It can help you to do the memory collapsing automatically. You just need to care about creating the pointers you want it to access and manipulating the computation on this list of pointer arithmetic, which we'll introduce later. Let's start from the CUDA kernel integration. So this is an example. So for example, we try to implement our fused addition and redo kernel. So this is very after we learned our last module, this is very simple, right? So we try to map this thread ID and the block ID into the index, and this index will be used to access different data in our matrix. And after we define this kernel, we will need to define the kernel launch. So this is the reason why we define different like thread block and the grid specification, and we pass this into this fuse redo and this custom kernel we defined before, and we try to use the Python PyBind to bind this kernel into our, for example, the Python front end we want to integrate with. So this is one way, the CUDA kernel. So as I mentioned before, the most of time you're spending on this custom CUDA kernel development. And there are two ways. So for example, PyTorch, they actually expose API for you. Let's say if you have a CUDA kernel you have a custom kernel written in CUDA, you just need to specify the name of the function and the file, the source file, and they can do the just-in-time compilation. And another way is more like traditional. You can use the setup tool to do the compilation before you use it. And the other way, as I mentioned before, is to use Triton. And as I mentioned, CUDA kernel development is very time consuming. So you can basically use this Triton kernel to do your constant kernel implementation. So the advantage of Triton is, first, it's easy to program, and second, you can still get decent performance in most of cases, in most of the operators. So the key idea behind Triton is it abstract away the low-level details. For example, you will not have the fine-grained control on different thread ID. You will not have this concept. And they will do this memory coalescing, shared memory synchronization, and tensor core scheduling, everything automatically for you. This Triton was proposed actually in 2019. There's a paper from Harvard. So they proposed this Triton C. And later on, the first author, the PhD student from Harvard, they joined the OpenAI. So OpenAI decided to support this Python front end for this Triton C. So later on, OpenAI pushed this DSL a lot. So the link is the official documentation. So this is just some history of Triton. So the first version of Triton is the Triton C. And later on, for commercial purpose, they introduced the Python front end. So as I mentioned before, the programming execution model of Triton is, because they abstract away this thread idea, so we call it single instruction, multiple data. So in this Triton kernel, although they don't expose the use of thread index and thread block index, the idea is still very similar. So in Triton, instead of controlling threads and thread blocks, they actually try to control multiple program instances. And this program instance is actually an analogy to the thread block. So what you are doing, for example, in here, you will get this PID. So the PID is essentially this instance ID, which is corresponding to the thread index we use in our CUDA program. And for each instance, they are trying to manipulate on a block or a tile of elements. So the key idea here is once you get this PID, the ID of your instance, you try to create a list or an array of pointers, and this pointer is corresponding to a block of tiles, and you try to apply some computation on this block of data. And every time when you got this pointer, you use the TL load and TL star to do this computation. For example, here you got this A plus offset, which is the pointer of the data you want to manipulate. So you load this data, and you do this computation, and you load it back, you store it back. So this is just we will introduce this kernel in detail, but this is just give you a high-level understanding of how it looks like. So the high-level philosophy is you are not trying to manipulate in the fine-grained thread level as what we did in CUDA. Instead, you're trying to manipulate in, for example, the instance, and the instance is analogy to a thread block. Okay. Yeah. So let's start from the first example. So for Triton, so I list 3 examples from the official document. But if you are really interested in this Triton, I encourage you to read the official document, because I think this programming language will be extremely useful. Let's say in the future, if you're doing some machine learning system job, and you only have limited time to develop the kernel, so Triton might be one option for you to do this fast development. So the first example is vector addition, so which you already covered in CUDA, right? So the idea here is, so first of all, every time we define this custom kernel, you need to add this decorator. And next, you need to get this PID to get the instance ID. So recall, in CUDA kernel, the first few lines, we're trying to assign this thread index to different matrix indexing, right? So this is very similar in Triton. You got this program ID as a PID, which is the ID of your instance. And then you create a list of pointers. So in here, let's say you get this PID, and this PID is actually sorry. Let's say you have a data, like let's say the total length of the data is, for example, 16, right? And what you're doing here is you try to divide these 16 elements into 4 chunks, and each chunk corresponding to one instance. So, for example, if you have you separate them into four chunks, and you try to link each chunk using one PID. So, for example, here is PID 0, PID 1, PID 2, PID 3. So in here, for example, you got PID equal to 2. So what you're doing is you first look at what is the starting point, starting address of this instance. So you got this block start, and you multiply with this block size, which means, let's say your PID is 2. So you need to multiply 2 times, because in here the block size is 4. We mentioned each chunk is length with 4. So you already iterate, but there are 2 blocks before this current instance. So you multiply this 2 times 4. So you get this starting address, which is corresponding to here, the start block. And you try to create a list of pointers. For example, here so this addition is basically the broadcast addition, which means when you add this starting address with this list of pointer, and what you will get is, for example, this in here you got 8, right? And here is you got a range 0 from block size, and after this addition, what you get is a list of pointer. For example, 8, 9, 10, 11. So this is the list of pointers you will get, and you pass this list with this mask, which is used to kind of control the boundary. For example, if your elements only has, for example, 11 elements or 10 elements, perhaps after this masking, this will just become 0 or false. So it's kind of used as the boundary check for this mask. And let's assume there's no boundary mask. So you still have this list of 4 pointers, and you try to pass this offset plus with the starting point of x and starting point of y, and you try to get the data you get using these pointers, and then you do this calculation and you store the data back. So this is very simple, right? So instead of controlling the multiple threads, what you are trying to do is you get this instance ID and you create a list or a 2D vector of pointers, and you try to use these pointers to load the data and then perform the computation. So this is the programming philosophy of Triton. It's very easy. And the next example will show a slightly different programming philosophy, because in this example we try to allocate the consecutive elements into one instance. And in the next, before we go to next example, so there are some extra functions you need to define. The first one is you need to define this helper function. If you recall in CUDA, once we define this CUDA kernel, we will need a launch kernel. We will need to launch function, right? We need to pass in these kernel hyperparameters, for example, the grid dimension, a block thread dimension, all of these things. This is the same for Triton. And if you can see here, so this grid is analogy to the CUDA grid. So it can be three-dimension variables. And you also need to do with this memory allocation. If you recall in our CUDA, we also need to do this. It's very similar. It just, you can see that you can treat them as the Python version of your CUDA program, and you pass these kind of kernel parameters into this kernel, which we show in last slide. You pass in this kernel hyperparameter into this kernel and kind of do this computation. And one of the key features I want to highlight here is called auto-tuning. So this is kind of one of the most important feature introduced in Triton. So if you recall, at the beginning I mentioned for different GPU architecture, they might have different shared memory. So which means if you try block tiling, the exact size of the block might be affected by the available shared memory you have. So for different GPU iteration, you might need to set manually different tile size. So in Triton, they actually help you to do everything automatically. If, let's say, you try this, you tell this program, okay, let's try the block size, different block size, for example, 128, 256. So for different block size, they will try on the target GPU and select the optimal one for you. And this is what we call auto-tuning. And it's not just limited for block size. You can also introduce other parameters. And in the next, we'll see a slightly different example, which is the fuse softmax. And recall in the first example, what we already covered. So we kind of allocate or group consecutive data into one instance. However, in softmax, we will introduce an idea called persistent kernel. But let's just look at this example first. So this is a naive implementation of softmax in here. So let's say you don't do any fusion. You don't do it's just basic, you can see this basic PyTorch implementation. And this is an example how it was executed in your GPU, for example. So this is your global memory, right? And then you have different operations. And as I explained before, for each operator, it will need to transfer data back and forth to the global memory. So in this case, if you don't fuse this softmax, the total memory traffic is 5 times m times n plus 2 times n reads, and also for write. So I will leave the detail later, but this is the drawback of this naive implementation. And what we want to do is we want to fuse all these operators together. So that's the reason why we have this kernel, which is called shared fused softmax kernel. So this part of knowledge is a bit advanced, so it's not required. If you don't understand, don't be worried, because we are not assessing this Triton programming in your coursework or coursework or exam. So just take it as further reading. So here we use the number of stages. So if you recall in your computer architecture course, we have an idea called double buffering, which means we can overlap the compute with the communication. So this number stage is basically used if, let's say, you set this number stages 2, which means they kind of enable this double buffering. So which means if you have a CPU core, so instead of have just one buffer, you can have 2 buffers. So when you try to load your data when we try to do this computation, this is your compute core. So when you try to load the data from the first buffer, you can also use the second buffer to load the data from the global memory. So that means you can kind of overlap the compute with your data transfer. So this is the number stages. They actually enable this double buffer. And the next thing is, recall what we having before is, if we have, let's say, this is the naive implementation. So this is the one way of grouping the pointers into this one instance. So previously we grouped these 4 consecutive elements into one instance, right? So in here, they introduce another idea called persistence block. Because in this example, every time, let's say if your total number of data is changing, you will need to change these parameters to group different pointers to one instance. So in this example, what they're doing is, equally, let's say you have 4 instances, equally divide this these 16 data by the number of instances you have. And for example, if you have 4 instances, right? And instead of assigning each, like say 4, originally in our last example, we have these 4 consecutive data loaded or grouped it into one instance. However, in this piece of code, what they are doing is, so they try to assign the first element in this first chunk into one instance. Let's say instance PID 1, PID equals 0. And then they kind of have a jump. So they have a stride to kind of group the pointers. So they kind of assign the first element from the second chunk to this PID. So it's more like stride access or grouping of these pointers to this instance. So that's the reason why in here, you can see here, they use this row step. So let's use that row step corresponding to the number of thread blocks you have, or the number of instances you have. And they do with range. So they kind of do this strike and group different pointers from different chunks together to do this. The benefit of doing this is it doesn't matter like how many data elements you have. You can always equally partition different data by the number of instances you have. So this is the idea of Triton with the fused softmax. And the last example is matrix multiplication. Perhaps we don't have enough time to go into very detail, but we will come back to this matrix multiplication example in our tutorial question, and we'll explain how to do this, what we call as the pointer arithmetic. So in Triton, the common way to implement the matrix multiplication is what they call here block program. So the idea is very similar to the Flash attention. You basically partition your big matrix into multiple blocks, and you do this block program, which means to calculate, for example, this is your A, this is your B, this is your A, and this is your C, and you do this matrix multiplication between A and B, right? To get this small block, the first block in your C matrices, what you need is you will first need to load the subtile for A, and also another subtile from B, and you do matrix multiplication. You get the 2 times 2 intermediate result. And in next round, you kind of evict these 2 by 2 elements, and you load the next 2 by 2 matrices from A and B respectively. So this is the idea they have. And the key idea here is, let's assume the block size, for example in here, the block size is f times n. So if you look at the pseudocode, it's corresponding to if you look at the pseudocode, we translate this into like the pointer arithmetic. So it's corresponding to the line above at the top of this line. And so the key idea is we try to map this PIDM and PIDN. So previously, PID is 1D vector, right? So we have this 1D vector of PID, which is 0, 1, 2, 3. So this is traditional way. But actually, you can also try to get a 2D PID. So for example, here is your n PIDN, and here is your PIDM. This is 2D vector, 2D matrices. So basically you have, for example, 0.0, 0.1, 0.2. So you have the 3 times 3 instance array. So in here, what you got is you will use this PIDM and PIDN to kind of, as the index, to leverage your instance. And according to this PID index, what you're doing is you're actually trying to get the address of the corresponding block. For example, if let's say you want this mixed PID number, to access the corresponding data or block in A and B, what you need to do is, for example, in here, as you can see, we first calculate offset. So offset equals to PID m times the block size m. And if you recall what we covered before, so we multiply this PID with the block size, which means how many blocks were already before the current block. And we get this offset along the A dimension. And we pass this with this list of block size, and we get a list of offsets, which is basically corresponding to this, the starting address of this red part. So this is actually here, right? And the reason why we multiply by stride AM is because the data rate might have some stride. So this is the way how we get this, what we call the vector of rows as the offset. And we can do the same for the vector of column. This is the purple line. So we do the same. For this, we got the vector of starting columns, the address of starting columns. And we do this, as I mentioned before, this is the broadcast addition, and we get m times n pointers. This is a 2D point. And we add them together, and this is the address we want to access in the matrix A. And we do the same for matrix B. So this is the pointer arithmetic in a 2D Triton example. And the next is, once we got all these pointers for matrix A and matrix B, the next is we need to perform the computation. So for the matrix A multiplied by B, let's assume we have the dimension. Let's say in here we have A, which has the dimension m times k, and B is the k times n, and the dimension of C is m times n. So what we need to do is, in the innermost loop, we need to iterate through this k dimension, right? So that's the reason why in the innermost computation, we have this computation. So we kind of move the pointer along this k dimension to like kind of accumulate the results. And we do this iteration through k dimension, and then in the outer loop, we iterate through the other two dimensions, m dimension, n dimension. We have the full picture of this matrix multiplication, and then we write the result back. So this is the matrix multiplication. So we go through it very quick. So there's one more thing. It doesn't matter if you don't understand now, but I will introduce more in our tutorial. So it means when we get this PIDM and PIDN, how we can do this mapping is very important. For example, if you use this two line of code to do this mapping, basically the computational order will be like this. You load A, one row of A, and you keep loading different columns of it. So when you try to calculate the read and write, number of read and write access, it's actually 9 plus 81 blocks read and 9 blocks write. So this is a naive way. We feel like this is not very efficient. If you recall, in 2 lectures back, we introduced the block tolerant, right? So this is not very efficient because we load this one row from A, and we row one column B. We do a computation, and we just do the computation for block B once because there's no data locality. So we are not reusing this one column B anymore. So this is the worst case. To mitigate this problem, another way is we call supergroup block. So it's very similar to the idea we have in the memory collapsing, which means instead of loading one row from A and all different columns from B, what we're trying to do is we try to load 3, for example, 3, this group 3. Let's say we load 3 rows from A and three columns of B, and we keep caching all these 3 rows and 3 columns and do all the computation. And this kind of significantly reduce the block read and block write. So we will reiterate this example in our tutorial. But because this is not related to our exam and coursework, we'll just briefly go through it. And starting from next, so the reason why I want to introduce Triton is I feel like this knowledge will be very useful if you really do machine learning system job related work after your graduation. So I put the slide to the official document here. So feel free to go over different examples. For example, we have the vector addition, few softmax, matrix multiplication, what we already covered. And they also have different optimization, like the layer normalization, fuse attention. As you can see, so the Triton actually lower the programming difficulty, and you can still get decent performance. So this is the key I want to convey. And let's have 5 to 10 minutes break. And starting from next hour, we'll do AI hardware, which is basically this GPU and how this historic array works. Yeah, thank you.
To the top.
For CUDA, so for exam, there's no CUDA or Python.
We're gonna eat between one.
It's the CUDA, because the main reason is the exact behavior of this CUDA.
Having enough time. No, honestly, my scholarship. I need that exam. That's a lot of money.
Oh yeah, you don't have as much control.
That's when
Every way they I guess that's cool.
I don't know.
So the AI type.
Like law with average library.
They have
I'm gonna write this
If we finished like 5 minutes ago,
yeah, that's
what modules are you doing?
Just like nice and raw.
So far,
Like my personal tutor and your data
right.
I was looking at all of like the students and people in there.
Like I was one of the AI
That's so
that would be cool. Like I like.
just like
I guess I'll have to do something AI related. Like AI.
when you don't really fall, you won't just skip over like proofs, for example. You actually explain stuff like that. The lecture can be a bit at home. You've had other 3 modules.
the US for a while. Like a lot of really I can see it.
Exam was fun.
Like implement like
It's basically saying
it's like
when you exactly. Because the lectures are very fast paced. And it's like I know you one part.
You like it? Yeah.
It was so dry.
In my undergraduate, I had friends that when I was like with housing.
I mean, like you save
Little surprise. Buying as much food as I would, you know, like
Like a connection.
yeah.
His first time in London. Just went out on the weekend.
I feel like Cornell is just like so.
His tuition like $65K American dollar. American.
Go bunch.
We'll
go for a short.
No, but I'm surprised.
Yeah, I think you're right. Like, I looked. I just did like a continuous.
You're international. It's like,
How far does it take to go?
You're gonna go back.
See, there's like 200.
Cornell like undergrad.
The train.
Or I guess it's masters in engineering.
They're not too bad. You talk often.
it was harder.
What is that? Wow, 10K more, and then like I have to pay for it. I was like,
What's the time difference?
No.
I think like in
say that because I got notes.
comes like
There was some sweet stuff.
This one? No. January 6th.
Actually, like, I wish I was like a UK citizen.
But
Nice pay. I guess for you though, it's like yeah, you're. My parents are definitely like.
Yeah. He's gave me.
actually like
Yeah, turn that as a
My parents.
And it's also. Tuition, like my tuition, housing was like 30K and my actual tuition for the grant.
yeah.
Nothing wrong with that.
Who's gonna supervise?
Oh, I see.
It's more in like I went. I don't actually think
Like, technically, I can.
It sounds so fun.
Like background of like I feel like I stuff.
Flight modes.
Hate dry conversations.
Oh, you want to go?
Oh man,
You want to go with research?
just like
Oversaturated.
exactly. It's really rich, and then
I can't do the hybrid. It was like,
Yeah, exactly.
your project.
I can't even.
Patient.
Oh yeah, that's
Because it's
That's what it turned into.
Some kind of
in the US.
That was a reset.
sounds kind of cool.
Like the front end.
No idea.
I'm doing like a PhD or anything.
Mouse is when it came out of my mouth the wrong way. I said something from the universe.
Exactly.
Do you know what you said in the video?
From the three people stop He's civil. Because I did some mechanical engineer from
You know, it's like people have that like, oh, you gotta take societal consideration. I think it's just
like a small I didn't even think they're nuclear. I know, like,
Then I didn't go to Slivert till I was doing 1:30 because I wasn't.
Berkeley business. There's like
yeah, it's a real shame. Someone actually originally in US. It's crazy. So happens.
You used to having it crazy, right? Winter break.
I was a little nervous for
I think
presentation.
I like to.
I've never been able to enjoy my break. The most when I because exams are stuff and I don't see this.
that just came out. Tradition should
Nothing.
like the other
It's the place I'm leaving.
Then you wouldn't imagine having.
That's why I'm happy. I was like, you know what you have done? You show me open the door.
I mean, it's a 10-point
It's like here.
I'm trying to see if I can.
And I told him he was in the residence for him, and I was like,
no, you're gonna have it.
so
I was worried.
no, I know.
No. That was what.
It would be like this whole period.
Yeah.
The next semester you're focusing on the new one. It's quite
I like it.
I don't know. Dude, starting next year. I know, but then I saw like the guy that posted
And then
I'm going to study transcription. I'll tell them to come.
bring up fun.
Yeah, let's do it.
I remember having a new group. Was it in
I have like Nigeria. You just come. I don't know if it's like, what are you gonna do? So you need to prepare. I know.
I was like, relax.
never hear it.
It's just gonna be the hardest thing.
Yeah. Are you
He's like manga on manga.
UCLA was 10 weeks straight.
Are you?
I don't think it's okay. I mean, we don't get as much.
Like in our first meeting, I think like not a scam.
Hi, I invite you.
I don't think we'll take.
Hi, welcome back. So I hope you take a good rest. So some students are still confused about this recomputation, so I want to explain it a little bit more. So if you look at the pseudocode, the only part that we transfer back to the off-chip memory, as written in the last two lines in this forward pass, is your output matrices here, and all the statistics for your algebraic aggregation. So this is all the data stored in your high bandwidth memory, your global memory, and this for loop is just the forward pass. And when you do this backward pass, and because in your high bandwidth memory, you only have these output matrices, and you don't have these probability matrices. So you need to do this recomputation to get this P, because you need anyway needs to update different like the gradient involved different tensors. So this is the reason why I mentioned here is a recomputation that is required in the backward pass. But this is not the key, like the key idea of the Fletcher tension is still first fused operation, and the second is called the algebraic aggregation, or they decompose the softmax, try to decompose the data dependency along the row dimension. So okay, so let's move to our second part of today's lecture, which is the AI accelerator. So some people might be confused. Now we already have GPU for AI. Why we still need domain-specific accelerator or customized accelerator for AI? So the reason behind here is the energy efficiency. So the GPU consumes a lot of energy when they do the AI training and inference. So in the longer term, it will still raise some environmental concern about like the carbon emission. And also, it's always good, let's say, because you consume more energy, it's better to make your hardware more energy efficient. So that's the reason why we have this domain-specific architecture as an active research topic. And actually, all the industrial players, for example, Meta, Microsoft, they invest a lot of money in building their own AI chip. So example is, for example, Google, they have their own TPU. Samsung, they have their NPU. And Tesla, they have their Dojo, which is another AI chip. So in this example, so in today's lecture, we will only cover systolic array, which is a core computational engine in Google TPU. And after your understanding how this TPU works, and if you look at the other accelerators, you will find they are basically very similar. So it's always the overall architecture of Google TPU or other AI accelerator. So if you look at their hardware architecture, it will be always the key part is this matrix multiplication unit, which is used to compute the core matrix multiplication. And they will, after this, they will have different activation function units and different normalization units. And here they use pooling, because pooling was very popular in early version of convolutional neural network. So in here, so they also have this pooling module. So you will realize the architecture of AI accelerator are mainly followed by, starting from a matrix multiplication unit for math computation, and followed by different special function units. And they kind of form as a data flow, so they connect each other together. So today we will introduce this matrix multiplication unit, which adopts a very classical computer architecture, which is called systolic array. And systolic array was invented back to 1979. And if you look at the author, so he's also the author of Triton C. So this is a bit history. And the idea of systolic array is, instead of designing my processing unit or my matrix multiplication unit in one row, can we just arrange this systolic array in a 2D array? So which is better for your interconnect complexity, which we'll introduce later. And the benefit of systolic array is it's very suitable for regular workloads. For example, the matrix multiplication, you kind of have the regular two matrices, and you do this matrix multiply and accumulation operation. So let's just start from, to introduce this systolic array, we first need to know what is the issue of a naive implementation for matrix multiplication. So let's start from a simple example, 3 times 3 matrix multiplication. So if we perform this matrix multiplication in the inner product manner, so what we will do is we get each row from matrix A and each column from matrix B. So this kind of leads to a very naive kernel design. For example, this is your computation you want to perform. And let's say your right side is the architecture you design. And in this dot product manner, in the product manner, so you have one row from A and one column from B. So you kind of use different buffers to cache different rows and different columns from matrix A and matrix B. And to ensure perform the right computation, let's say you have a 1D vector of processing engine. So this processing engine is basically perform multiply and accumulation computation operation. So now the problem is how to feed this data buffer, the data, into all this computational engine. So to achieve this, we will need to have this interconnect network. So let's say we need to connect buffer A to the first 3 processing engine such that we can perform the corresponding matrix multiplication to get the result. And this is the same for buffer A1. It needs to connect to 3 PEs. And the buffer A2 send 3 PEs. And at the same time, because you are trying to multiply the data from A and B, you also need PE to connect with buffer 0. So which means each buffer, you will have the finite degree of 3. So this is just a simple, starting from a simple example. So can you observe any issue of this design? Let's say we goes up to 1,000 times 1,000 PE. What is the problem? So the problem comes from this interconnect. Let's say if you have 1,000 times 1,000 PE, it will make your interconnect very complicated. Because one buffer, A0, it needs to connect to hundreds of PEs. And in the early stage of chip design, so this is not very good for achieve a high clock frequency for your hardware. So the problem comes from the scalability, as I mentioned before. So if you, let's say, goes up to 1,000 or 10,000 PEs, this is not a sustainable way because this interconnect will become very complicated. And you have 3 drawbacks. The first is high finite, which means for this buffer, in this 3 times 3, it only needs to connect to 3 PEs. However, if you have thousands, you might need one buffer to connect to 100 or 200 PEs. The long wiring and the complicated fan-out will kind of affect the timing design of your hardware. And the second is the long interconnect delay, because in a chip design, you are basically place memory unit and compute unit in a 2D plane, you're not able to overlap them together. So this is a traditional 2D chip design. So let's say if you put your buffer here, so to kind of have, let's say, 100 Ps, you have to place a P very far from this buffer. So it will kind of increase the interconnect distance to affect your timing bottleneck. And this kind of complicated interconnect also increase the area and the power, because you need to have more wires to do this interconnection. So it kind of consume more power in the area. And so that's the reason why we need a more efficient hardware design, which is called systolic array. So the key idea here is, instead of connecting PE to each buffers, we can try just to connect the PE among each other. And the idea is, for example, we form this 3x3 PE as a 3x3 array, 3x3 2D array. So we only kind of feed the data at the edge of this 2D array. So basically, we only feed the data from, let's say, the data from the buffer A1 will only go from this PE00. And then the data go through PE00 will kind of propagate to PE01. So you are not connecting your PE01 directly to this PE buffer A0. So this is the whole idea of a systolic array, because you kind of make your data propagation very regular and also reduce like the problem we mentioned before. So you don't need to connect your PE to all the buffers. And what you are doing is you try to rely on the data flow among different PEs in this PE array. So later on we will use an animation to illustrate this idea, but from a high level, this is the whole systolic array design. You have, instead of have the 1D PE, or like lying as one line of PE array, you have 2D array. And instead of connecting all the PE to all the buffers, you only connect, for example, the top line and the top line and the leftmost column PE to the PE buffer. And let's look at this animation. So let's look at this animation. So basically, at the first, so you can see the data is actually propagate through this systolic array. And at the first clock cycle, in here, you can see the buffer A0, B0, flowing through this P00. And in the next cycle, so the data received at the first clock cycle at P00 will propagate to the second P. So it's kind of, you are trying to flow in the data through. It's more like a wavefront. So you use this way to kind of propagate your data. And one more thing you need to be careful is about, you need to add some offset in your data stream. So let me explain why. So for example, if you can see here, at first clock cycle, only the buffer A is feeding data to P00. And buffer A1 is not feeding data. So the reason is, we need to ensure the correct data are multiplied at the correct timing. And because in the first cycle, the B00 is still in the PE00. So the data is still in this PE. So if you feed the data into PE10, which means the element A10 will only multiply with 0, right? With nothing. And so that's the reason why in the first clock cycle, you only feed A00, and the buffer A1 will start to feed the data in the second clock cycle, because it needs to wait the B00 to coming from up to down to get the correct answer multiplied together. So this is one thing you need to be careful. So this will kind of get into this offset. So I think this is more straightforward. So for example, basically they're just different direction, but they're the same, right? So you need to have some offset where you kind of feed the data in. to make the data at the right timing and get multiplied with the right number. So this is the historic array. Let's go back to see what is actually contained in the PE of this historic array. So if you kind of see when we zoom out with this zooming with PE design, so you can see one PE is usually contain one input register, which is used to cache the data from the left-hand side. And we also have this weight register, which is used to cache the data from the up dimension. So you can see here, if you can see this animation, it basically hold the data. For example, here at the first clock cycle, it will need a register to hold the data. And in this example, at the first cycle, input register is holding A00, and weight register is holding the data B00. Clear, right? And apart from this register to cache your data, to kind of store your data, you also need different computational units. And in this example, we use the multiplier and accumulator. So, but you can also replace this compute unit by other function unit if you feel like you want to extend your historic array for different other different other computations. For example, exponential operation. So this is very flexible, and this historic array itself only represents an idea of designing your PE array. It's not just limited to the matrix multiplication. And the benefit of this historic array is the scalability, as I mentioned, because you don't have the long interconnect, right? And you don't have this long wire. They try to squeeze all these compute resources and memory resources in a 2D plane. And in here, I want to introduce 3 different stream flow or data flow of this historic array. So they are basically, let's going back to the example we visited before. Let's say you have a matrix multiplication, and you multiply A with B to get multiply A with B, and you get C. So the first data stream, what we call as C state AB string, which means we take these 2 input matrices as the input data and streaming into this historic array to get the corresponding result. And this is exactly what we show in this animation. Right. And this is exactly what we're showing in this animation. So we basically accumulate, the C is actually basically accumulate and stay in this P, inside this P. So the result of C is not flowing when we do this accumulation. So this is the first data stream, or the string flow, which is called C string, C state, AB string. And you can also do some other string flow, and the second one is A state, BC string, and you can also do B state and AC string. So the idea of the later 2 is, for example, if you have a large amount of, let's say you have the B matrices, and the data locality of your B matrix is very high. So what you want to do is you don't want to flow this B, you want to keep this B inside your PE. So basically, in here, you just cache this B, and you kind of flowing your C as the input data. So at the beginning, so the C is all initialized as 0, and through this streaming up and streaming left, so the data will kind of accumulate it. So if we use these, for example, B state and AC string, so the connectivity of these basic PE units will also need to be changed. Because in here, let's say this is your C, and this is your A. And basically, you will need an extra register which hold your B. So the B will stay at the same PE all the time during you do this computation. And for the C, it will not fit into this multiplier because the multiplier is connecting input register and the register holding B. And if you have the C streaming in, you will just put this and add them together using this accumulation. This is accumulation. Using this accumulation accumulator. So if you use different data string, you might need to change this basic P unit. But you can also design your P unit to make it reconfigurable to support different data streaming or stream flow. So this is the basic of historic array. So here, the other thing I want to mention is different scenarios and different matrix multiplication with different dimension. They are actually prefer different string flow. So in here, I compare the output stationary sister array with the weight stationary sister array. So the advantage of output stationary array is you don't need to preload your weights. So if you recall what we have here, so in the weight stationary, we need this B to stay in the PE, inside the PE. So that means we need extra clock cycle to preload all this weight to this PE. However, in contrast, so in this output stationary, we don't need to preload any weights. We just the register inside the PE can be just initialized at 0, right? There's no preloading effect, and it's better support for large reduction dimension. Just remember, if we have A multiplied by B equal to C, this is a matrix, and a reduction dimension represents the innermost photo. So if you have a large K, which means if you want to implement this large K matrix multiplication to this weight stationary, you need to do some tiling because in this weight stationary, you try to map these B matrices into this historic array. And let's say if you have large K, which means it has some requirement on the physical shape of your historic array. So that's the reason why output stationary is better if, let's say, you have large reduction dimension, which means kind of remove or avoid a lot of limitation when you map the weight matrices on this physical historic array. And the drawback of output stationary is you need some extra cycle to get the output. So when for example, in the animation I showed before, so when the result is ready, when the A times B is ready, so you need to streaming out this output. And there are different ways to streaming out this result. First, you can design a bypass wire. For example, you can just connect this PE to your output port. But you will also introduce some interconnect problem. So a common way is when the result is ready, you just flow it using the register inside the PE. Like when for example, in this clock cycle is ready, so you just flow down. So it means you will need extra clock cycle to stream all the output results from your historic array. So this is a drawback of output stationary. And for weight stationary, the part of weight stationary is if, let's say, your weights has the high data locality, by caching these weights inside your PE, can kind of exploit this data locality. And it's more like the caching, right? So you cache this input data in your PE, so you kind of reuse it again. You don't need to kind of load it from the global memory and transfer it back. So this is the advantage of weight stationary. And the choice of output stationary or weight stationary in historic array is an active research direction, because for different matrix multiplication with different shape and different data locality, they always prefer different data flow. So we have in my group we have a student working on this direction. So we're trying to adaptively choose the best string flow or data flow for the historic array according to the matrix shape of different workloads. So this is the historic array, and this historic array is only used for matrix multiplication. And you might wonder how this historic array in Google TPU is used to perform the convolution. Because in convolution, you remember you have a styling window, right? So this is not straightforward to implement in this historic array. So there are two common ways to apply this, to perform this convolution in matrix multiplication unit or this historic array. The first one is called imaged column. So basically, in the hardware, you have an extra hardware unit, or you can kind of perform this imaged column operation in CPU to kind of transfer this convolutional kernel into a 2D matrices. And if you look at this animation here, so this is your 2D, this is your convolutional kernel, and each kernel is like 2 by 2, right? And you keep striking through different location to get different, to get the corresponding weight matrices. And the basic idea of imaged column is, for example, in the first clock cycle, the data you want in the red map is 1, 2, 5, 6, and you just copy this in here, and again, for at the first cycle, at the same location for different color map, you get different data, right? This is the first cycle. In the second clock cycle, when your starting window strikes to the next position, you also copy all the data required. So in the second clock cycle, what you need is 2, 3, 6, 7. So here you copy this data in here. So it's basically it try to flatten this 2D convolutional kernel into 2D matrices. And the drawback of this problem is obviously, so you have a lot of data duplication, right? So for example, these 2 appear multiple times, and these 3 appear multiple times, right? So this is the drawback of imaged column. Although this is very general, and but it will introduce a lot of actual memory overhead, because you are trying to have the data copy multiple times when you do this computation. And another drawback of this image to column operation is if you design a specific hardware in your, for example, in your TPU to perform this image to column operation to convert this 2D convolutional filters into this 2D feature map, the logic of this image to column hardware unit itself is very area consuming. So if you look at the first version of Huawei's Ascend AI accelerator, so they report nearly 20 to 30% of chip area was spent on this image column operation, which is not very area efficient. So that's the reason why some other AI hardware also observe this issue. So they also design another way to do this sliding window data streaming, which is called line buffer. So the basic idea of line buffer is you will have 3 memory bank, row by row. So they will kind of connect it together. So this is your line buffer. So one line representing one memory bank. So at the beginning, so the way they are connecting together is here there's a mux. You can choose. It can streaming out to as the output or connecting to the next line. So this is the hardware function unit. There's a mux here. To choose, you should output the data, or you should streaming the data to the next line, next memory bank. And the basic idea of line buffer is, for example, you have this convolutional kernel in, right? 1, 2, 3, 4, and you're kind of streaming your data in, and you have this 1, 2, 3, 4. After 4 clock cycle, you load all this data. At the beginning, you don't choose to output the data. You choose to output the data from in the first memory line buffer to the next line buffer. So which means when more data comes in, the 1, 2, 3, 4 will move to the next line. For example, 1, 2, 3, 4, and you will have 5, 6, 7, 8 in the first line buffer, because the data is still kind of keep streaming So you kind of push this data to the next line. And at the same time, so let's say you have the 3x3 kernel, so you will also kind of push this one by another line. Let's say 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 8, 9, 10, 11. So you have this, and you know this is the right timing for you to output your sliding window. So at this time, when all the data is ready, you just switch this multiplexer to make this line buffer as output mode. So you just like streaming out these 3 lines of data in parallel. So this is line buffer. It's just designing hardware which emulate the sliding window streaming out process. And the drawback, or the advantage of line buffer is very efficient, memory efficient, because you don't have any duplication of the data. So when you compare this implementation, this line buffer implementation with this image to column, you don't have any data duplication in this 2D map. Right? This is making it very memory efficient. But the downside of this line buffer is it's very hard to make it very general. For example, if you have a kernel, let's say your line buffer was originally designed for 3x3 line buffer, you will have these 5 lines. Let's say your kernel is 5x5. So basically you need 5 line buffers connected together. But let's say if your algorithm is changing to the kernel 3x3, which means 2 lines of line buffer, they are wasted. So it's very hard to make it general, although it's very efficient. So these are the 2 implementation which transfer your convolution to your matrix multiplication that are representing different technical routes to implement your convolutional kernel on this matrix multiplication engine. And this is the reference, so it's not required you to learn in detail. So the first version of TPU, they only support inference, and the precision they support is just int8, multiply and accumulate. And in the second version, they try to support training as well as inference, and they add another different types of data precision called Brand floating point. So this is a new type of precision compared with the half precision floating point. And it basically can introduce 1.5 times energy advantage over like the IEEE standard 16 bits for floating point. And we'll introduce different data type and different precision in our next lecture. So we will introduce what is microscaling and what is block floating point and what is the brand floating point. So they have different formats. Like basically they have different bits, number of bits for exponent and mantissa. And in TPU-v4, the focus is shifting from a single chip design to a large system. So that's the reason they have these optical circuit switches to introduce for the networking. And one of the key features in TPU-v4 is this sparse core. So they realize in deep learning, because the pruning will introduce in our next lecture, it will make your matrix as the sparse matrix, which means if you have a matrix which contains a lot of zero, let's say this is 2 times 2, but you have 2 zeros in the diagonal, and you only have 2 valid elements, they call it the sparse matrix. And once you have this sparse matrix, so what you want to do is you want to skip the computation of 0 elements because they are wasting your clock cycle. So that is another feature called sparse tensor core. They kind of introduce this sparse tensor core as a core processor to kind of accelerate the sparse matrix multiplication. And the next idea what I want to introduce is scale up and scale out. So the scale up means, let's say you have one chip, and you want to use some like interconnect, electric interconnect, connect multiple GPUs together in one computational node. This is called scale up. It's more like a small scale how to scale your number of GPU in one compute node. So let's take an example of how NVIDIA do their scale up. So they use NVLink to kind of connect multiple GPU together, and they also use this NV switch to connect multiple GPU racks. So this is how the NVIDIA GPU is doing this scale up. They try to build from one single GPU to form a larger scale GPU system. And after the scale up, there's another idea called scale out. So the scale out is usually used, for example, the optical interconnect to connect multiple GPU nodes together to form a supercomputer. So, for example, NVIDIA, they have the infinity bands, which try to connect multiple nodes together. And as I mentioned before, GPU-V4, they introduced these optical circuit switches, which also help you to do this, like optical connection. So some students might wondering why we don't do like optical connection for short distance GPU connection. So the reason is, in one chip, all the signals, they are in the form of they are in electronics. So when you want to control your signal from electrics to optics, you need these optics to electric conversion. It will kind of introduce an overhead for this conversion, for example, power area. So for short distance, we'll always use the electrics interconnect. So here I show a concrete example how GPU scale up their system. So this is one chip design. So if you can look at, this is the high bandwidth memory, this is the compute core, this is their L2 cache. And also they have NVLink, which is trying to link multiple GPUs together. And they also have NV switch to connect multiple GPUs. So they kind of form this is the overall picture, like the high-level picture of the NVIDIA GB3000. And so they basically have 72 GPUs connected together using the NVLink and NV switch to do this scale up. And another extreme of a scale up, which is kind of advanced knowledge, is called wafer scale computing. So which means, let's say, in GPU, so you usually have the chip area of around just 200 square millimeters. So this is for traditional GPU, it's very small. And the idea of wafer scale computing is you can have a very large chip that are connecting together. So basically the idea comes from, if you're from the EE background, you know when you do this chip tap out, or chip manufacturing, you will have a term called yield rate, which means which kind of a matrix to reflecting how many defective chips you will kind of have in one run if you kind of tap out multiple chips in one wafer. So usually in the chip tap out, this is your large wafer, and all the chips will fabricate on this large wafer. And let's say you divide this wafer into multiple chips. So the common way to improve the yield rate, which means to avoid the defective area, is you design these small chips one by one. So this is the traditional GPU manufacturing process. You kind of divide this large wafer into this small chip area. And the reason behind this is the larger your memory, the chip area is, the more likely you will have the defective chip. So that's the reason why most of the commercial or most of the mature chip manufacturing, they have the small chip area. So they want to improve their yield rate. Yield rate means how many, it's kind of reflecting how many defective chips you can produce by, let's say, producing 100 chips. So the idea of wafer scale computing is, so instead of having these small chips and take it out, so they kind of put everything into one wafer. And even if, let's say, some of the chip may become defective, so you can still use your advanced compiler and routing strategy to kind of avoid using these defective chips. So this is the very advanced knowledge about the wafer scale computing. It's very popular in research direction. So as you can see, Cerebras is the leading company manufacturing this wafer scale chip. And you can see that compare this Cerebras chip with this traditional GPU, the chip area is much larger. And in terms of the number of cores and transistors, the Cerebras also contain much more. And the last idea we want to introduce is reconfigurable hardware. So as I mentioned multiple times throughout our lecture, so we have two types of reconfigurable devices. One is FPGA, which representing a fine-grained reconfigurability, which we'll introduce later. And also we have the coarse-grained reconfigurability. So they are kind of shaping or forming the trade-off between the flexibility and performance. So this is the compute architecture of FPGA. And you can see the key component is, first is this CLB. So it's basically lookup table. So you can kind of reconfigure this CLB to any logic you want. And you also have this memory. You also have this DSP. So for example, you can use this DSP to do high-speed multiplication or addition. So the idea of FPGA is they put all this general reconfigurable fabric and general like different memory and DSP, and try to use the idea called programmable interconnect, which means you can connect any CLB to any DSP to any memory. So this kind of make your FPGA very flexible, because even after your tap out, for example, in ASIC, you are not able to change the function of your chip. But in FPGA, you can actually reconfigure this CLB and reconfigure this programmable interconnect to kind of to design it with any function you want. And this CLB is actually like representing a kind of reconfigurability with the bit level control, because each lookup table can be used to any Boolean function you want. And also this flexible interconnect routing network make this FPGA very, very flexible. Let's say if you want to connect the CLB at the rightmost to the leftmost. So this flexible interconnect also make it possible. But the downside of this CLB and the flexible interconnect is because it needs to keep the connectives between, for example, the leftmost and rightmost CLB. So it actually consumes more area than just have some one-to-one connection. So this is the FPGA. And one thing I want to mention is, there's a series of work actually from Imperial EEE. So the first one is LockNet. So if you search this paper, they try to use this lookup table as the basic computational unit to do this processing, and they keep updating the configuration of this lookup table to do this backpropagation to update this configuration. And the other is FPGA-based data flow accelerator. So the last few things I list is all the application of FPGA for AI. And the second thing is FPGA-based data flow accelerator for machine learning operator. So if you remember, if we have this GPU, the common way we are doing is we kind of fuse several operators together, perhaps just 5 operators or 7 operators. But if you look at the whole network, it might contain, let's say, 50 operators. So the idea of this FPGA-based data flow accelerator is they try to cache all the intermediate results to on-chip memory. So it kind of forms a data flow. So for first physical layer, they have a physical compute units in FPGA, and they connect these different layers engine one by one. So if you are interested, you can look at this paper called FPGA COFNet. And the first author of this paper will be the invited speaker in the last week. So he was the former student at EEE, a PhD student at EEE department, and then later on he joined Samsung AI, and later on become the lead of machine learning system group, team lead of machine learning system group at Samsung AI. So I invite him to give a talk on the latest trend in industry for machine learning system. And the last one is CGRA. So basically, you can see here, instead of have the CLB, they have the more, they kind of replace the CLB and the lookup table with the more coarse-grained reconfigurable unit. So this M means memory. So PMU means programmable memory unit. And they also have programmable compute unit. So it's not a lookup table. So you can only have a limited choice for the reconfiguration. For example, you can reconfigure this unit as matrix multiplication and reconfigure this unit as other operations, but it's not a general Boolean function, which loses some flexibility and generality. And if you look at the connection, it's also less flexible than the FPGA, because in FPGA we have very large gray area for this reprogrammable interconnect. Okay, so I don't want to keep you for long because I think we are running out of time. And this is recap. So the first part, we introduced the custom kernel integration. We introduced the flash attention as an example, and this is one of the key part you need to learn. And the second is we introduced how to do the custom CUDA kernel integration and Triton kernel integration. We used 3 examples for Triton. And for different AI hardware, so we briefly introduced what is the six-story array, what is the basic principle behind six-story array, and what is scale up, scale out. And we also introduced different reconfigurable hardware, which they are representing different trade-offs. So this is the end of today's lecture. Thanks for coming. See you on this Thursday.
No point, right? Yeah, for sure.
We're just like, I think I'm just gonna send them an email. The class just ended.
Wednesday, sending class.
Guessing you're not gonna go.
We just like say we're here. He lives like in Monroe.
How come you weren't there last time?
I love like
To rearrange a meeting for like 3 weeks.
You go, no. Yeah, there is probably about 3 minutes until it ends.
Yeah, just let me know. I will be here. If you are too busy, maybe next week.
I know tutorial.
not doing that.
就会有 description。
Yeah, 2 minutes. This is just 5. Just 5. I think I'm just gonna go first. Let's say you have. Let's draw 3 times 3. So this is the.
It will be 1, 2, 3 like this.
Yes. And then when you kind of use. Yeah, it will be kind of control your multiplexer to connect to the next line. So which means there's a controller to control this line buffer, and he knows what is the row number, and at the 4th clock cycle, it knows it's time to feed these outputs of the first line buffer to the next line buffer.
But 1, 2, 3 we don't fit it in for the 1, 2, 3.
You already fit into this through list, right? What do you mean? Like,
But how can it know? Like, for example, if I have this, and I just want the 1, 2, 5, 6. It should be 1, 2, 4, 5 for the first
Yeah, that's what I'm saying. It will require very complicated control logic.
For it to
Yes, so this control logic will know, for example, what is the kernel size and what is the feature map size. And it will kind of do some calculation by this control logic.
Does it need, for example, does it need 1, 2, 4, 5 here, or it can be like flowing from here, and maybe we need a few cross cycle to do
1, 2, 4, 5. Where do you get this?
like because we want the number.
Yeah. You can also have 1, 2, 4, 5. In this case, so once you fit in one elements, you will kind of in next cycle you will fit into the next line to get this 1, 2, 4, 5, right? So it's not 1, 2, 4, 5. It's actually it's actually 1, 2, 4, 5.
Oh,
this
okay.
way. Yes.